Hello everyone, this is Muhammad Javed, lecturer Mathematics International Maritime College. Outcomes for the lesson are a reverse of differentiation, we also call it integration, and then we apply the table of integrals while doing some example on integration, and at the end we'll introduce definite integrals and we'll apply on some example as well. So what is differentiation in reverse? This is a function. If we take derivative according to the rule sheet, it comes to x. So if we look at in the reverse direction, it would be meant that the reverse of 2x will be x square, or the integration of 2x will be x square. Integration of 2x is x square. It means this is a kind of cycle. They are reverse to each other. If we have derivative, differential, we can give answer of integral. If we have integration, then we can give value of differentiation. So there are certain. Now some example for more elaboration of the concept of integration. The derivative of x square plus 4 is 2x, then x square plus minus 5 derivative is 2x, and again 2x. 2x, 2x, 2x. It means the integration of all these three things which are same coming different. 2x one time x square plus 4, another time it is minus 15, the last time it is 0.5. So we need to cope this situation, and integration of 2x, we can say that this is x square plus c. So in the first case it is 4, in the second it's minus 15, in the third it's 0.5. Well, we formally write the integration with this symbol which we call integral symbol. So integral symbol to x plus dx. Now some terminologies regarding integration process. The integration of 2x is equals x square plus c. So in this expression, this symbol is known as integral sign. After the integral sign, 2x we call it integrand, and beside it dx we call it differential symbol, and we write it dx. Then there is a constant of integration. So they are always the part of this integration, reverse of differentiation. Like the table of derivative, we have table for integrals always as well, and we'll use this onward. Here an example, x7 we are doing with the help of table, a screenshot of the few rules of the formula sheet. x7, I think it is comparable to rule 3.1. x7 and xn, they are same. So 7 plus 1 divided by 7 plus 1 plus c. Concept of integration will come all the times. Rule 3.1 is used, and final answer comes as x8 by 8 plus c. Part B, where we have to take differentiation of the final result. The final result is x8 by 8 plus c. So according to the differentiation rule, 8 will be reduced by 1, so it will become 7, and 8 will be multiplied with x, so 8x7, and divided by 8 was already there, and c is a constant, so integration of constant is 0x7. Another example from the book, example 1.3, the opposite side I attached for a part of the formula sheet. So cosine of 5x, if we see, it is like rule number 6 part B, part 2. So cosine of 5x, and according to the rule 6(2), which is k with x, and k here is 5. So cosine of kx dx equals sine of kx by k. Cos is converted into sine, and it will be divided by k, which is 5. So this is integral. Another example, I think rule 5(1) will be used here, because it is not only x. Part 2 will be used, because this is not only sine x, it is sine kx, and k is 1 by 2. So it will be divided by 1 by 2, so according to rule 5 second, which comes minus cos of kx by k, so k is here 1 by 2, and sine will be converted into cosine, and minus, and definitely constant of integration will be produced like the previous questions. So simply we can write this minus 2 cos of x by 2. Another example, this time the variable is small t. So sine of 2 pi by capital T, they are something common, something constant. So the variable of integration is t. Solution. So 2 pi by t, they are k. Going for rule 5(2), sine will be converted into minus cosine, and it will be divided by k. Constant of integration will be produced. So its answer come out is, after simplification, 2 pi by t, which is in the denominator, will come in the coefficient of cosine of, and we will take reciprocal of it, and plus constant integration. Another example, this time we don't have variable, it is just a constant number, a fixed number 12, and for this I think the rule 1 was there. Yes, rule 1. When we don't have any variable, it's constant, so x will be produced with it, and of course constant of integration will be placed all the time. And this time even we don't have any fixed number, but it doesn't mean there is nothing. There is one value, which is 1, so it is equal to 1, and it is a constant again, so 1x or x will be produced with plus c. Another example, when the integrand is the sum of two functions. For this we have a rule 20. If you see your formula sheet, I have uploaded the formula sheet both for integration and differentiation. You can pick from the Moodle. So f of x and g of x are two functions. There can be plus, there can be minus, two cases, but we have plus in this example. So this will be equal to the sum of two integral, f of x dx plus g of x dx, because we have plus. If it was minus, then it was supposed to be done as f of x minus g of x integrals. Okay, So two separate integrals now with plus. Rule 20 is used. Integrating the first term with the help of rule 3-1, actually this is not 2, 3-1, and sine x integral will be minus cosine x, and in both the cases constant of integration will be produced. Rule 3-1 is this one, and rule 5 sine of x dx equals minus cosine of x plus c. Well, after arranging, constants can be taken out separately, and the constant sum will be again constant, we know it. For example, 3 plus 2 is again 5, which is a constant. There is a big example from the structural engineering bending moment in a beam. I've taken this from the book. So the weight is putting pressure or load on the beam downward, and definitely after some time it will start bending the beam. And if we read it carefully, L carrying length L is the length of the beam, W is the load per unit length, the bending moment is M when it will bend down like a curve. So the bending moment is M, which is a measure of internal stress caused when the beam is loaded. So this bending moment is actually stress in it. M varies with position x. This moment is different at different places because the bending will be more in the middle, the bending will be very less at the ends, and slowly and gradually the bending will be increasing toward the center of the beam. It can be shown that the bending moment is related to the shear force V. Now what is V? V is the change in rate of change of M with respect to x, and if we integrate it, or if we V is actually W by 2L minus 2x. This is modeled by the structural engineer, and hence as V is the rate of change of M with respect to x, so we write for V as dm by dx, and this is derivative. So if we want to know the M actually, so we integrate it. So a reverse of differentiation is involved here. Okay, so solution. So actually we are finding this integration. There are two integrals, L and 2x, but note that only x is the variable, the remaining all other things are here now constant. So look, in the first integral, WL by 2 constant, I took them outside, and the second integral 2 was constant, went outside. Now using rule, so first one doesn't have any number, I produced x according to rule 1, I think, or rule 2, and the second one has got x, so its power will be increased and divided by 2, and then simplifying it, after further simplification, further the x term I made them separate. LC1 is a constant, 2C2 is a constant, so their answer will come again a constant, so I'm writing for them C3. So our final answer is this, and this is the bending force in this structure. So this is a practical use of integration, or the reverse of. Now the concept of different integrals. So this is definite integral. It has got limit this time, and we say it is the integration of f of x from a to b. X equals a is the lower limit, and x equals to b is the upper limit. Generally we don't write x with them. A and b will be understood that they are x values. So when you evaluate a definite integral, the result will usually be a number. So this time we will get some number, not an expression like in the previous reverse of differentiation. Let's take an example from the book. Yeah, look, the upper limit is 4, the lower is 1. Applying the rule 2(1) is used. According to that, concept of integration will be produced, and don't forget to write the limits. So one time we will plug in the upper limit value for x, then minus the lower limit value for x. One time we write x value 4 in the first bracket, in the second bracket we write the x value 1, and there will be subtraction between them, simplifying them, and this one is plus c and minus c. So it is suggested that onward we will be not writing in constant of integration, because in definite integral they will be cancelling each other all the time, and this is a constant number. So answer from x square from a to 4 integral is 21. Another example, sum, and again sum, but there is slight difference. The limit from 1 to 2, and in the second case the limit is 2 to 1. So let's see, do they make any difference? Yes, of course they will make difference. So integrating, applying the rule, plugging in the upper limit value and the lower limit value. This time I use concept of integration, but we don't need to use them because they will be cancelled out, and the answer is 10 by 3. Plus 3 and minus 3 will cancel each other. Second, when the limits are changed, the same way the upper limit will be plugged in first in the first bracket, and the second limit will be plugged in the second bracket. This order is important. First of all, upper limit first, and then in the second bracket the lower limit will be placed second. Constant c's will cancel each other, and the difference is only minus. So this is a difference. When the limits are interchanged, I minus sign will be produced. So this is a rule actually now, that a to b can be made b to a, but sign negative will be produced with it. So take care of this rule. Civil engineering, another example. Consider the tank of water as shown. D is the height of the tank, LW, they are actually same, but taken LW because this is a cuboid. Length, height, width are all equals. The pressure P at the depth H was shown by the Pascal in the 17th century. Now H is any height, D is the total height of the tank, and H will be the small h will be the height of the water anywhere. It could be in the middle, it could be little up from the bottom, and it could be near to the top, and even it can be the total, but it is a variable changing. So Mr. Pascal took the pressure rho gh. Rho is density, g is the rho is density of water or the liquid, and g is the gravity of the acceleration, gravitational constant we call it, and h is the height. Well, and this gravity is 9.8 meter per second square. With the knowledge of hydrostatics, it can be shown that the force exerted on the wall of the tank, now the water is putting pressure on the wall of the tank. This is going to be the definite integral, and so this is the force exerted on the wall of it. This is actually the force. So let's calculate this force, evaluate this integral, and show that the force on the wall is the same as the product of the average pressure and the area of the wall. So let's go to the next slide. Added in a half space there, so we are going to integrate it, and note that z is the variable, so only rule will be used in the integral where z is involved. Okay, so it comes dz, because d doesn't have any z, it is a constant. The second rule is used, I think, yes. And then z square plus c. I'm using c, but you can neglect it from here. Okay, in the next step I am plugging in this rho gw. They are constants, so I put them outside, and upper lower limit, different brackets, they are done. After calculation it comes like this. Now let's come to part B. The pressure at depth is rho gh, any depth. The pressure at the surface is 0, and pressure at the base of the tank, the whole height of the tank, is putting pressure on the bottom. The average of the total and average of the total pressure and the pressure at some height, it is always taken as rho g d. So area of the wall is dw. If we look at the force, what we did earlier in part A, it can be expressed, the answer can be expressed rho gw d square by 2a's. We separate dw from it,